So welcome. So today we are going to talk about AthenaX, the streaming processing platform at Uber. So before we dive in, we are going to quickly introduce ourselves. I'm Hao Hui. I'm a senior software engineer at Uber, and I've been in the data domain for a while now. I'm a PMC member of Hadoop and Storm, and Bill is also a senior software engineer at Uber. So Uber's business is fundamentally a real-time business. What Uber tries to do is to provide a transportation service from point A to point B on demand in a very reliable way. This is actually fundamentally very dynamic. One very good example is the Uber Eats product that we have. So in Uber Eats, just in case you don't know, so you can order food, just open your phone, and then Uber will actually deliver the order to the restaurant, and then once the order is ready, a driver partner will actually pick up the food and deliver it to your home. And then now you can start eating. It's actually quite dynamic in terms of marketplace. So as you can imagine, there will be more orders from lunchtime or dinner time compared to work hours. Our driver partners would drive around the city at the time the food is ready. The distribution of driver partner might be very different. So this is actually a fundamental, very real-time and dynamic business. What are the challenges here? We can actually categorize them into two categories. The first part is the infrastructure side of the challenges. So there's a lot of focus on reliability and scalability. So the common question that we need to answer is, okay, how to provide 4 nines of SLA, at least once processing, scaling the system to handle billions of messages, and how to take care of multiple petabytes of data per day. The other parts of the challenge is more from the solution part. There's a lot of emphasis on productivity. So we are actually very data-driven. Majority of our employees use SQL very, very actively. Spark is another example. So we make our decision based on data. Another interesting fact is we have a lot of employees that comes from a non-technical background. So for example, they are pretty good at looking at data, making decisions, making marketing campaigns, and so forth and so on. So they would like to have the ability to answer questions in real time or near real time because our business is fundamentally very dynamic. So what is the right abstractions for them? So for example, Flink teaches us how to do reliable and scalable streaming processing, but for people that don't come from a technical background, that may or may not be a good fit. So that's another part of the questions. So the other part is actually integrations. So there's how we're going to integrate the whole system with in the Uber ecosystem. For example, how to do data management, discover the data you want to look at, how do you manage your job and reporting and so forth and so on. So here's what we do, what we used to do. I mean, probably a year or two ago. So we have input, we have output. If you want to build a real-time application, you write some code, possibly pick a framework, for example, Flink. Then you can do reliable and streaming application by connecting the inputs and output together. It basically helps you to solve the problem of making sure things like reliable and real-time streaming by picking the right framework. But it's actually very framework specific. And it's very ad hoc in terms of how we manage our jobs. So different teams might solve the same problem in slightly different ways. And at the end of the day, as a streaming platform team, we have to support all of these requests. And that becomes very much a nightmare for our side. So here's the AthenaX approach. So instead of asking our users to write code, now we ask them to write SQL. So the key takeaway here is actually when the user writes SQLs, then we actually models everything as a generic table. So table, in contrast to traditional database terminology, which only means a collection of rows, in AthenaX, table essentially means how the streaming application can interact with the external system. So for example, in this case, it could be means a Kafka, MemSQL, Cassandra, and so forth and so on. And then AthenaX would take the SQL that actually built on top the abstraction of generic table and compile them to pretty much the code you have written previously. So the advantage is now the business logic and framework is now decoupled. So we actually give our non-technical user a way to tap into the real-time data in a much more scalable way. I mean, scalable particularly in terms of how you can write jobs, how we can effectively support the jobs. Because now everything is SQL, we have unified integration and management. So we can support much larger number of use cases with much lower support costs. So to quickly recap, before we actually dive into any details, the key thing that I would like you guys to take away from the talk is you can actually write SQLs to build streaming applications by using the concept of generic table. AthenaX delegates the problem of how to build reliable and scalable streaming pipeline to Apache Flink. The key value add is now you can develop and deploy streaming application in production in hours instead of weeks. So here's the agenda of the rest of the talk. We're going to quickly go through one example. Then we go through how we actually do it in real world in the Uber Eats use case. Then we'll talk about the implementation and current status. Then we'll conclude. So here's one example. So assuming we are in the Uber Eats business and you want to have a real-time dashboard for restaurants. So as you can imagine, you have some orders coming in. We can put it into a Kafka topic. So some orders, someone will place an order, sometimes the order is finished or delivered, and so forth and so on. And the objective is you take this list of orders. You want to have a dashboard having some ideas on what are the average meal preparation time. So that if your meal iteration time actually spike, probably something's wrong. Maybe in your kitchen, maybe in the system, something's wrong. So there's a couple of interesting things to look at. I mean, we are talking about average preparation time, but what are the average means? What you are averaging at? So in real-time domain, what we usually do is define a window. A window essentially is just a period of time. So for example, in this case, might be something includes 3 orders. So, and more intuitive way to say it is, for example, last 15 minutes, last 30 minutes. So if you continue to look at it, it might go slide as the times go by. So this is essentially a sliding window. So if you need to actually write code, that could or could not be complicated. But I will actually present you something like SQL. You can be done in this way. So essentially here you have a meal ID, basically the ID of the meal, and then average preparation time. And then you group by 2 things. One is the meal ID. The other is actually the hop cost is actually specify what window it is. So this hops cost is actually means a sliding window, which has 15 minutes, and each slice is 1 minute. So essentially, you are talking about something like what is the last, what is the average meal preparation time for the last 15 minutes? So we can make it a little bit more complicated. For example, if we are able to figure out the expected time from 1 or 2 meals and from each meal IDs, and then we say, okay, if the expected time is actually much smaller than the average time, we should send our alert. So the way it works is you plug in the same Kafka input, but instead of putting into a dashboard, now every single record we send an RPC and fire an alert. So that way, table actually means something more generic than a collection grows. It can, as long as you do that, you suddenly have the power of building all the kinds of streaming applications, for example, doing alerts and other things. So key thing, table actually more generic than an store. So next, I'm going to hand it over to Bill, and Bill is going to talk about the extended ETD for Uber Eats use case.
Okay. So here I'm going to talk about the Uber Eats story with AthenaX, especially on the ETD. So as Hao mentioned, so Uber Eats is a Uber food delivery service. It makes you ordering food from your favorite restaurant, as smoothly as you request ride with UberX or Uber Pool. But it's different with Uber Ride. So it's a three-sided market, including eaters, restaurants, and driver partners. And also it raises a new request for real-time metrics. For example, ETD, the S-time to delivery. You need to show the ETD to the users. And also you want to show the dashboard of transactions to restaurant and do demand forecasting also to the restaurants. So among those real-time metrics, the ETD, I think, is the one affects the eater's user experience the most. The reason is if you know when your food will be delivered to your door, then you can make an arrangement of your waiting time to make your to make you use your time more efficiently. So the question is, how could we predict the ETD? So one of the ETD, there's very key metrics is the time to prepare a meal. How long will the restaurant spend time on bake your sandwich or grill your pastas? So we need to train a model or learn a function, to take all the stats as input and returns the preparation time. And this model will need to be periodically updated based on the data. So if we get this function, then we can use this function to predict the ETD for current orders. So AthenaX plays a very critical role in the ETD service. It's used to extract features for both learning and prediction service. So here is the architecture of the ETD service. So whenever you make an order on the mobile phone, it will publish some events into Kafka. And also if any status change of the order, so it also publishes events to Kafka. All these status change events will consume by AthenaX. So AthenaX will calculating features based on these events and writing two copies in two different places. First copy will go to data warehouse, which is Hive, and it will use it to train the model in the future. And the other copy will go to the feature store, which is hosted by Cassandra. And these features, the feature in the feature store, and combined with the model in training the model trained by the machine learning algorithm, will combine to consume by the prediction service to give you the ETD. So you will see here the feature engineer doesn't need to write a single line of Java code. He can just specify a few lines of SQL statement and then click some button on the AthenaX framework. Then the extraction job will automatically set up, and the monitoring and dashboard, all kinds of things automatically there. So this is a story of Uber Eats and AthenaX. Then I hand over the presentation back to Haohui.
Okay, thanks, Bill. So now we are going to quickly go through implementations and current status and conclude. So the way it works is like AthenaX basically takes two major parts. I mean, it takes SQL and catalogs as input, and then it put both SQL and catalog into a query plan and optimizer. And then there's the other part is how do we manage our jobs. Once the AthenaX compile the job into Flink, then you just let go and let Flink to take care of all the management. So for the first part, when we do query optimizer planning and optimization, Flink and AthenaX actually combined to do compilation and code generations. So we are actually actively contributing back on the Flink APIs. So it's a very common usage pattern in a database world. We take a SQL, make it into a logical plan, then it translate and compile to a Flink applications. We heavily leverage the Volcano planner in the Apache Calcite. We are going to talk about it. We actually don't have time to talk about it in presentation, but I'm pretty much happy to talk about it offline. So the real challenge for this part is actually how to expose the streaming semantics there. So for example, one thing we have been talking about for a lot of Flink literature is what's the difference between process time and event time, and how we are going to expose them to SQL layer. That's actually a very interesting problem to look at. So the other part, we actually make the decision to making sure AthenaX is a self-service platform. So customers or our user can actually make their jobs just run in production end-to-end all by themselves. So there's a couple of features we have to build. For example, catalog management, job management, monitoring, resource management, and auto-scaling, and how to recover from failures if there's data center failures or something so on. So current status, we have some jobs already running in production already. We have really promising results, and so we're actually starting the process of full-scale rollout. We're actually on top of Apache Flink 1.3, which haven't been released yet. We support projection, filtering, footprint, and users-defined functions. Unfortunately, no support for streaming joins yet, but we are actually actively looking at those, and we may or may not be able to add it in 1.3 timeframe. We make a lot of contribution back to the community, such as good Windows support. That's the example that you just have looked at in the very beginning of the presentation. Some stability fixes on the Kafka consumers, and we are pretty much adding table abstraction into Cassandra and JDBC as well. This is work in progress. But the key thing is we plan to make everything available in the upcoming 1.3 release. That's probably happen in a month or two. So hopefully you guys should be able to use all these features as well. So to conclude, AthenaX allows our users to write SQLs to build streaming applications. So in order to actually do that, the key thing to think about this model is to treat table as a very generic concept, just more than something that you would typically think in a database. It can mean something like RPC, or even Thrift, or Cassandra Elasticsearch, and so forth and so on. It's just more than that. So if you think in this way, you suddenly have the ability to build streaming application using SQL, and we see a lot of productivity boost here. We have seen people that's outside our group that make streaming applications from development to production in just a matter of hours. So the AthenaX approach is, just to quickly recap, we basically saying, okay, you can write SQL on streams, and we make it as a platform. The key to make it as a platform is we allow our users to self-serve themselves all the way from development to production end to end. And that's it. I'm ready to take questions.
Can you talk about the catalog and the schema aspect of the stream? How do you derive it?
Yes, so we have an in-house version of schema registry, centralized schema registry. So essentially everything that comes into Kafka in this pipeline has to have a schema. But the schema our schema is actually pretty complicated. Most of them are actually nested and optional. So the way the schema registry works is everything is arrow, and we make sure it actually can be able to plug into the AthenaX system.
expect the schema to be there?
Yes, yes, yes. So that's at least the initial plan. There's work on dynamic schema, but we don't see a lot of asks yet.
Hi, so you support UDF. UDF may seem like a black box in your code. So how do you handle the optimization? Things like optimization when there's UDF in SQL.
Good question. So in terms of optimization, we don't actually optimize the UDF, but we do a lot of optimization on, for example, lazy deserialization, because we have a really huge schema, and we just deserialize the field that we want. And things like traditional push-down filtering, and we do this, but not UDF. Yeah.
What is the scale of the Flink running in your system?
Today is much smaller. We're actually in a pilot mode now, but we actually have a plan to move all our streaming processing job, which already running in Xamsa, to the Flink cluster. The original Xamsa cluster have hundreds of nodes.
Since you said that it was a key insight, could you clarify what the generic table concept is? It so that in that one it's each order. Like how do you manage like what tables are available?
Yes, that's actually a great question. So if you look at this slide again, so a generic table essentially means a way for input and output. And yes, you are right. You have to have a metadata and catalog management to tell our user what, for one particular table, what does it mean? Does it mean a Kafka topic? Does it mean a MemSQL table or Cassandra table, and so forth and so on? So that's the part we actually built to tell our user, okay, for this table in AthenaX actually means something else in the external system.
Okay, we're limited in time, so thank you very much.
Yeah, we're happy to take questions offline.
Other questions, maybe offline.
Yeah.
Thank you.
Thanks.